Okay, let's get started here. So today we have one little small thing left to go with discriminant analysis. Then we'll start a new topic, nearest neighbor classification. Again, project number 2 is due on Friday at noon. So with respect to Save Our Stats, unfortunately I don't have really anything good to say. Other than the Faculty Senate will have a no confidence vote again on Tuesday, I think it's at 2:30 over the East Campus Union. Are there any questions? Okay. So the main way that we determine whether or not a discriminant analysis method is good is we look at how accurate it was, or conversely, you could say the misclassification rate. And we looked at 4 different ways to measure it. One way in particular was to split the data set into 2 randomly, where one of the data sets, or one of the data sets that resulted from the split, use that as your model building or training data set. And with respect to discriminant analysis, what that means then is you estimate your mean vectors, you estimate your covariance matrices on that model building training data. Because that's all you need to do that's all you need for discriminant analysis. Then you apply this discriminant analysis rule that you get to the other part of the data that you get split off. That other part's often referred to as a validation data set, a calibration data set, or a test data set. And so when you apply it then, you look at, well, how good did it work in classifying everything, or predicting everything, or finding the correct groups, however you want to put it. So the last thing that I want to talk about then in this section is, well, how could you randomly split a data set into 2 parts? And so that's what is on about page 49 or 50. Let me actually go over to 10 for this. Okay, so with the place kicking data set, there's actually 2 parts to it. There is a model building, and there also is a test data set or validation data set. I guess I used the word validation. So place kick is the model building, valid is the validation data set. Okay? At the very beginning of this program, I read them both in. Now what I want to do is put them together and simulate how one could actually split the data set into 2. It won't be the same exact 2 that we used, but to split it into 2. So to combine these 2 data sets together, the easiest way to do it is to use the rbind function in R. R stands for row, bind means combined. So what's going to happen is since I put place kick first in this code, place kick is going to go right here in your data frame, and valid is going to go right underneath it. That's what the format will be. I'm going to put that into an object called all.data. And so there's the head, and here's the tail of the data frame. Okay? Notice there are 1,707 observations. And a way to automatically count that is to use the n-row function R to say how many rows. So I'm going to put that into an object called n.all. Sorry, I've left my mouse in my office, so I might be a little bit slower trying to maneuver on the keyboard and screen here. Okay, so what I'm going to do is split the data set into 2 random parts. There's a number of different ways to do it. I'm going to use a very common way here. Since I'm doing it at random, I like to be able to have a way to reproduce my results. So I'm going to set a seed to begin with. So I say set.seed 9819 for the lack of a better number. Then I can the way that I'm going to do this is as follows. So I have 1,707 observations. How about I just randomly select from those observation numbers, 1 all the way up to 1,707. Once I get my random selection observation numbers, I can tell R, okay, pull those rows out of my all.data frame. Okay? So, to sample integers, there's a function called sample.int. The first argument is called little n, and if I just put capital N dot all there, what that's going to tell R is I want to go from 1 up to 1,707. How many of these observation numbers do I want? Well, let's say that I do an 80%, 20% split. Now, again, there's not a set rule about how much is in your model building, how much is in your validation data set. There's not a set rule. I wouldn't have more than 80% in the model building. That would be my limit. I would want to have at least 50% in my model building. I just happen to choose 80% here. And so what sample size do I want? So let's take 0.8 times n dot all, and I get 1,366. So that's how many different observation numbers I'm going to sample from 1 up to 1,707. So if I run this and put the results into obs.num1, let's look at the first few. Let me make this a little bit bigger too. The very first observation I'm going to pull out of all.data will be observation 1,119, for example. Now, I also need to tell R, okay, which observation, so that will be going into my model building. But I also need to tell R which observations is going to go into my validation data set. So basically what I need to do is look at those numbers from 1 to 1,707 that I'm choosing, and then say, now put all the opposite numbers into another, in this case, a vector. How can I do that? Well, if I execute 1 colon n dot all, I will get a vector that has all the numbers from 1 to 1,707 in it. Okay? So indeed, you can see that. Now I need to somehow tell R which numbers I want for my validation data set. So actually, let me just do this to help emphasize the process. So what do you think this code's going to do that I have up here? 1 colon n dot all, I said n dot all, parentheses, okay? And then brackets 1 colon 5. Excuse me? Yeah, first 5. Okay? So basically 1 colon n dot all is a vector. And I want to pull out the first 5 elements. Now, if I were to do this instead, what's going to happen? Exactly. And so I'm going to use that same idea then here. So obs.num1 contain my observations for my model building data set, but I don't want those. I want all the other ones. So that's why I put a negative there. And so how about if I execute all this code again? Note that the head of obs.1 starts with 965. I think earlier I showed it was something else. I think it's because I didn't hit the seed number. And so now we can see for the validation data set, the first observation I'm going to pull out of all.data is observation 13. Okay. Now, let's work with all.data. For the row numbers, I put obs.1. obs.num1, put that into something called place kick 1. This is actually my model building. And then For the validation, I use obs.num2 for the rows of all.data. And let's just take a look at all this, what happens. Oops, I guess I can run it all, doesn't matter. Notice 1,366 observations in my model building, 341 in my validation. Notice the first observation is 965 in the model building. It's 13 in the validation data set. So that's how you can split two data sets at random using some code. Any questions? Okay, so there's one very, very last thing that we won't talk about that's in the discriminant analysis notes. I mainly put it there because the other person who mainly teaches this course, he will talk about this topic. I choose not to so I can move on and do other stuff. There's something called canonical discriminant analysis, which you can kind of think of it as a combination of principal component analysis and regular discriminant analysis. Meaning, imagine, let's say, you get your principal components, and then you do discriminant analysis on those instead of the original data. That's the concept. It's not exactly what occurs, but that's the concept. Okay? Any questions? Okay, let's move on to nearest neighbor classification. So discriminant analysis is known as what's called a parametric procedure. So in statistics, whenever we have, let's say, some kind of underlying probability distribution assumption for your data, we often refer to that as being a parametric procedure. Now, those are obviously assumptions to say that I have a multivariate normal distribution. Often you don't like to make assumptions. And so a procedure that doesn't make any probability distribution assumptions in general is referred to as a non-parametric procedure. And so discriminant analysis is a parametric procedure, and then we're going to go way to the other end of ways to approach this problem, and we're going to look at a really strongly non-parametric procedure that gets away from those assumptions. Now, as I told you though before, discriminant analysis, despite its assumptions, often works very, very well. If, let's say, the assumptions are, let's say, approximately satisfied or close to being satisfied, discriminant analysis will typically perform better than this new non-parametric procedure that we are going to talk about. If, however, the assumptions of multivariate normality are really, really violated, then this non-parametric procedure may work better than discriminant analysis. So this non-parametric procedure is referred to as nearest neighbor classification. Notice the name, nearest neighbor. We've seen that name with cluster analysis. You will see a little bit of similarities because of that. And so nearest neighbor classification essentially works like this. Imagine you have an observation, and you look at all the observations. Let's say you have a scatter plot. You look at all observations that are close to it. Let's say the k closest observations. Maybe 3 of those are from, let's say, group 1. 2 are from group 2. Well, since there's more in group 1, how about we predict the classification for that one observation you're interested in? How about we predict that to be from group 1? That's all how it works. So to put it into more of a picture context, I guess it's just reiterating kind of what I said there. Suppose, though, instead we have 3 populations or 3 groups for our data. And we have two variables, x1 and x2. I denote in the scatter plot the plotting point for the actual observations denoted by the actual group or population number. And my goal is to predict what grouping I should have for the red dot. And so let's say I have k is equal to 1. So I'm looking at 1 nearest neighbor. Well, we see that there is one observation that's obviously closest to it. If we just think of, let's say, Euclidean distance, And so therefore, I would predict that red dot to be from group 1. Let's say instead I have k equal 3. Probably the next 2 closest observations are from group 2. And so since 2/3 of the observations are from group 2, 1/3 from group 1, 0/3 from group 3, I predict then that red dot should be group 2. That's all how it works. What if, though, k was equal to 2? And based upon how I labeled this here, 50% or 1/2 is from group 1, 1/2 is from group 2. So we have a tie. What should you do? Okay, one approach will be to use the distance, and we can see that it's closest to 1. Another approach that you will see often done in statistical software is that they will ignore the distance. There's ways to incorporate distance. We will not here in our class. But one way to do it is just to say, let's go to the next observation. So instead of k equal 2, we go to k equal 3. Okay, so that red dot would be classified as group 2. Another thing that can sometimes happen is that they will break essentially this tie at random. So it will randomly choose 1 or 2. So depending upon when you implement the procedure, you could get a different result. We'll talk a lot about that kind of stuff as we go along. Let me actually turn off my spell checker here. Now, similar to what we saw for cluster analysis, before you do nearest neighbor classification, you will almost always standardize the data first. And so while that picture that I showed you was not standardized, it's just easier to present it that way. So at first, so that's why I did that. And also it's just, even an example coming up, I won't as well, just it's easier to talk about. There are 2 main functions in R that we will be using. They are from the class package. The name class comes from classification. The first function is knn for k nearest neighbors. The next function is knn.cv, k nearest neighbor, where we use cross-validation. So what knn does is essentially like what resubstitution is. So let's go back to this plot here. Let's just say that this was my original data set. I didn't split it at all. And let's say that red dot I knew was from group 1. If I had capital K equal 1 for the nearest neighbors, what would you classify or predict this red dot to be? 1. You see the problem? Obviously, there's bias. Now, what cross-validation will do is what I had described to you to motivate this, and that is they wouldn't consider what the actual group is for the red dot, and they would use all the other observations around it. Okay, so let's look at an example. We're going to have another example with just 4 observations, similar to what we had with cluster analysis, but these will be 4 different observations. Let's first take a look at a plot of the data. I specifically chose the numerical values as what you see here on purpose to demonstrate some stuff about how this works. And so what you see here is that we have 2 variables, x1 and x2. We're just going to use Euclidean distance just for demonstration purposes. And we can see how observations 1, 2, 3, and 4 are, each of them has 2 observations that are equal distance from each other. So notice 1 is equal distance from the distance of 1 to 3 is the same as 1 to 2. We also have 2 populations here, a triangle population and a circle population. Now, how did I do this plot really briefly? I created a data frame that had those observation numbers in it. I used my plot function to plot the actual observations, where I set up colors for the plotting points and the plotting characters to correspond to the population number that we see in the data frame. I put a nice legend on the plot. I also put the actual observation number on the plot so that we can see which observation is which in terms of the number. I use the text function for that. And then lastly, I can use the dist function, similar to what we saw for cluster analysis, to find the distances between the observations. So for example, that distance between observations 1 and 2 and 1 and 3, it's the same. And the distance happens to be 1, Euclidean distance. Okay, so let's look at how KNN works. And we're going to use K equal 1. Now, this package that we're going to use, class, is automatically installed in R. So you don't need to go ahead and install it yourself. But you do need to say library class to say, hey, R, I want to use functions from this package. With the KNN function, there is an argument called train. This is where you put the training data set or the model building data set, whatever you want to call it. And notice how I enter it. Set 1, and then I say, let's not also include that third column. Why? That third column actually gives me my population numbers or group numbers. I only want the data itself that I'm trying to essentially build a mathematical rule about how to classify observations. So I only want that data. Then I'm going to test this out on the same exact data set for demonstration purposes. That's why this is resubstitution. And then lastly, I have an argument called CL. That stands for the underlying classifications that we already have, the populations, the group numbers. And notice what I do. This is where I include that third column. I have an argument K for how many nearest neighbors, and then prob equal true. What this will do is actually give me essentially the probability, or you can think of the observed proportion of the nearest neighbors to each observation of interest. And so this is what then is produced. So I put the results into NNC1 for my first try of doing nearest neighbor classification, or actually I'm using K equal 1. That's why I use 1 there. And the first thing that's returned to you is the actual predicted groups. So observation 1 is population 1. Observation 2 is predicted to be population 1 as well. Then what's actually returned to you is a little bit of an older R format for an object. And the older R formats often will have what's called an attribute associated with it. And the attribute here gives us the probabilities or the proportions for that group that was in the actual population, the group number that was chosen. And we can see that we have a lot of certainty because they all have a probability of 1. So if you actually ever wanted to pull out those probabilities, you can do that by saying attributes NNC1 $prob. I should back up a second here. Since it's not a regular kind of list that we normally think about, if I say names NNC1, I don't get a list of components like I would normally. But if I say attributes NNC1, then we get what we're used to seeing with that $. And so I get all the probabilities, for example, there. And so what I can do then is create a data frame that has the original data set, create a new variable called classification where I put the results from NNC1 in there. And we can see again, we got a perfect result. Now, of course, why did we get a perfect result? We're using resubstitution with k equal 1. So to classify this particular observation, I use that observation. Let's see here. Do note that prob argument needs to be set equal to true in KNN if you want to see the probabilities, because the default is false. Okay, we've already answered that question. Why will k equal 1 always result in perfect accuracy with KN? Well, because you're just using that same observation. So let's look at something a little bit more interesting. Let's say k equal 2, 3, and 4. So the only difference in the code here is I use the k argument with a different value. Let's see here. So with k equal 2, look at these probabilities I'm getting. So for observation 1, I am actually predicting that it should be population 1, which is correct. And the actual probability that I'm getting, proportion, is 0.67. But k is equal to 2. How could I get 0.67 then? It's because I have ties. So what happens is this. Observation 1, it sees that there's a distance between 1 and 3 of a distance of 1. Between 1 and 2, a distance of 1. It then says, okay, since I'm using resubstitution, I have a population 1 here, I have a population 1 there, I have a population 2 there. So 2 out of 3 nearest neighbors are population 1, so I'm going to predict population 1. That's how it works. And in fact, you will see the exact same thing happens for all the other observations too, because of how I chose them. What happens then for k equal 3? Well, the 3 nearest neighbors are, of course, the actual observation itself, this one and this one, and so we get exactly the same thing as what we got before. Yes?
Is there a way to tell it not to use itself as an observation? Because it seems almost trivial, whitelist to
Yeah, and so that's where knn.cv comes in.
Okay.
Now you might be wondering, why do we even talk about knn then? Well, it helps you understand how the function works to begin with. And also, at some point, you may have then a validation data set or test data set, then that's not exactly the same as the training data set. And so then this function can work for you. Also, sometimes it's helpful to teach from the perspective of what not to do. So now if I use 4 for my k, now we get a little bit different results. Observations 1 through 3 are predicted to be population 1. Observation 4 is predicted to be population 2. So this is the one that's different. Notice the probabilities that we get. 0.5 for each. Well, why? Well, there's always 2 observations from population 1 and 2 from population number 2. That's why. So then, how did this come about then? Well, this is where R then will choose at random what population to assign, because we had 2 probabilities that were exactly the same. That's how it works. Any questions? Well, let's now go on to knn.cv then. Let's use the exact, it's essentially the same exact code. But now I have KCOL, I'm going to use KCOL1 there, and I say knn.cv. This is what I get. Three of the observations are from population 1, predicted, and 1 is from population 2. Look at my probabilities. 0.5. You might be thinking, well, how can I get a 0.5 probability if I only using 1 observation? That's where the whole tie thing comes into play again. So we can see for observation 1, both observations 2 and 3 have the exact same distance from it. So because of that, then what R is going to do is look at both observations instead of k equal 1 and see that, okay, 1/2 of them are from population 1, 1/2 are from population 2. I have a tie. It's not just a tie in the distance, but a tie in terms of these probabilities. How does R handle it? It chooses one population at random. Notice when I go to k equal 2, I get exactly the same results as k equal 1. Well, because again, I'm always going to have that tie. Then when I go to k equal 3, well, this is what we get. Observation 1 is classified or predicted to be population 2. Same for observation 2. Looking for observation 3 and 4. They're predicted to be predicted to be the population group 1. So I get completely wrong results. Why? Again, let's look at observation number 1. We can see 2 of the 3 are from the other population. That's why. Okay. So, there are some really there were some details there. Like small little details. And I do like to take the time to go over those small little details so that you can see what's going on. Because, like when I first taught myself how to do this, I was like, this makes no sense. This is a small data set. Why is this happening? And if you get into the details, then you say, oh, okay, that's why. And so that's why I think it's helpful. So a question that you might be wondering right now is, how do you choose K then? We saw a similar thing with K-means clustering. How do you choose K? And what do we do then? Well, we constructed a for loop where we tried out K-means clustering for a set number of values of K. And then we use a particular numerical measure to help us make a judgment about which K to use. We're going to do a similar thing here. You could look at scatter plots of the data first and make a judgment about what K would be appropriate, but that's often very hard to do, especially if you have more than two or three variables. Even if you did principal components, again, it might be a little bit hard to do. And so again, what K is chosen by trying a few different values and seeing which produce the most accurate classification. So that's our numerical way to compare and make a decision. So now let's apply this idea to the place-kicking data set. So now we are going to be looking at how one would actually do this in practice. I read in my original data set, place-kick. I read in my validation data set as well. Let's say that I already had them separated to begin with. The first thing that I do with my model building data set, which is place-kick, I standardize. So I use the scale functions, what we've done before. Notice I do not include the 9th column. Why? Because that's where the good variable is. That tells me, is this a success or a failure? In other words, the grouping variable. It doesn't make sense to standardize with the grouping variable there. We are standardizing the actual independent variables, explanatory variables, to make judgments about the grouping variable. Now, here's where sometimes people can make mistakes. You might be thinking, okay, for my validation data set, I'm just going to standardize that with the actual validation data set itself. Meaning, let's say find the mean of the distance variable in the validation data set, find the standard deviation, and then use that to standardize. That's actually incorrect. Rather, what you need is to take the mean and the standard deviation from the model building data set. Because that model building data set is what's going to help guide you to do all the predictions for the validation data set. Now, an extreme way to think about why what I just told you is the correct way to do it. Let's say that you are on the sideline again of a football game. You have your computer with you, and the coach says, should we go for the field goal or not? So essentially, we have one X. That X may be 40-yard kick. It's windy. It's at the end of the game. You have just one X. You have one observation that you have to predict. That's essentially a validation data set with one observation. Well, you don't know what the end result is, but you can think of it that way. What is the mean? What's the standard deviation of one observation? Yeah. How are you going to find the standardized value if you divide by 0? Now, of course, then the data analytics group for the executive leadership team at UNL here that dealt with the metrics, having a 0 in a denominator of some kind of ratio, that was no big deal for them, or at least a possibility that it could happen. Yeah. So, this is why we need to find then the means of each variable, the standard deviations of each variable for the success group, for the failure group in the model building data set, and then use those numerical values to find standardized values for the validation data set. Okay. So, in the past, when we've needed to find, I'm sorry, I did misspeak there. Yeah. We're not going to do it separately for the success and the failure group. Okay. The reason being is because when you would apply this in practice, let's say that you're on the sideline of the football game again, you won't know if that's a success or a failure. So you can't break them up based upon those groupings. So I use the col means function to find the means of all the columns in my data frame placekick. I take out that 9th column again because that's my good variable, my population variable, my grouping variable. And so the average distance was 27.5. Notice what the averages were for the validation data set. Distance was 28. So it was similar. How about the standard deviation? So what I do is I use a function. I didn't think about looking or verifying this when I was going through my notes before class. Have we looked at the apply function before here? Yeah. Okay. So what I like to be able to do is apply the function SD to find a standard deviation to each column of my data frame placekick. And so the way to do that then is the X argument is your data. Margin equal 2 means by column. Just look it up in the help. 2 is column, 1 is row. And then the fun or the function that I want to apply is the standard deviation. So the standard deviation of the distances is 10.55. Okay. Now, to form all my standardized values for the validation data set, I'm going to create an object called z.v, v for validation. I use my scale function as I've done before. There's my validation data set where I take out the good variable. Now we have 2 additional arguments we haven't seen before. I can use the center argument to say, what's the mean that I should use for standardization? The scale argument, that's kind of weird to have an argument the exact same name as the name of the function. If I were to write the function, I wouldn't have done that, but that's what they did. The scale function basically says, what's that standard deviation that you're going to use to do the standardization? Okay? So let's first begin with k equal 1 to see how well it works. Again, this is how you would do this in practice. You should always set a C number before you run KNN or knn.cv because of how ties are broken at random. So always use a C number so you can reproduce the exact results. KNN, my training data set, model building, is in Z. My test data set is in Z.V. The actual classifications are that 9th column of placekick, my good variable. I'm going to say k equal 1, and let's actually see what the probabilities are as well. So what comes back to you then is the predictions. So in NNC1, we see that the first observation is predicted to be good equal 1. In our data set, good is either a 1 for a success, 0 for a failure. Now, if I want to also see how well this works with cross-validation, then I set a seed. I use knn.cv. My training data set is in Z again. I don't have a test data set because cross-validation uses the original data set itself, just removes one observation at a time. I need to say where the actual observed classifications are. K equal 1, prob equal true. First observation is predicted to be a success. So then we get to using my summarize.class function that we saw in the discriminant analysis section. So summarize.class, my original observed classifications for the data. I'm working with the validation data set now. Valid, take out the 9th column. I'm sorry. The ninth column of valid gives me my good variable, what was actually observed for the validation data set for success or failure. I want to examine how well then the nearest neighbor classification then worked, where the results were stored in NNC1. So this is what we get. For failures, I was able to classify or predict it correctly about 45% of the time. For successes, I was able to make the prediction correctly about 94% of the time. What's my overall correct classification rate? 87%. Now, for the cross-validation results, my original groupings, it's that ninth column of place kick. My classifications are in NNC1.CV, right there. Now I only get 26% of the failures correct, 90% of the successes correct. My overall correct classification rate is 83%. Now, generally speaking, I would have expected the validation data to do a little bit worse than the original data with cross-validation. The reason being is because that validation is completely separate. It just so happened here, the reverse from what we would normally expect happened. Why? Perhaps I'm speculating here, is because that validation data set's kind of small in terms relative to the number of failures in it. That could be why we're seeing this. So that's just for k equal 1. But again, we would like to be able to apply this in a situation where we choose the best k. The best k is the one that's going to give us the best accuracy. So how can we look at a whole bunch of k's? That's where we can do a for loop, similar to what we did with k-means clustering. Here's how this works. Let me actually come over here to 10. No, stop doing that. Stop. Okay. Sorry, I guess I had lost my place where I was in the program, so it just takes me a little bit to find it. And since I don't have my mouse, it's a little bit more difficult to maneuver. This is annoying. Okay, so again, I need to set a seed so that I can always reproduce the results. Let's go ahead and do that. Then I need a place to save the results. First, I'm going to create a matrix called save.results, and this is going to contain the results from the validation data set. It's a matrix. It's going to have 10 rows because I'm going to look at k equal 1 to 10. It's going to have 4 columns because I'm going to put in there the overall correct classification rate, the correct classification rate for the failures, also for the successes, and then as well I want to track what k was. And so what I'm going to do is I'm going to initialize a matrix that's that size, and since I'm initializing it, I don't know what's going to go in it yet, and so I just put in NAs. Eventually those NAs will be replaced by the actual results from the for loop. I'm going to do the same thing for the cross-validation matrix to save the results. And here's my for loop. Notice I'm going to say for k in 1 to 10. How about we just say k gets 1 here so we can step through it. So k is 1. Then I'm going to use the k&n function just like what we did before, where that capital K there is replaced by 1. Going to do the same thing with the cross-validation. And then let's actually use the summarize.class function to look at the classifications that we see there. I'm going to put that in an object called nnc.accuracy. Do the same thing for cross-validation. Then finally, the last two rows correspond to when I'm going to put the results into my saved matrices. I'm going to combine together the value of k, the accuracy for the failures, the accuracy for the successes, and then the overall accuracy. Just to show you, this is what we get. Notice what I did there, for example. Let's see here. nnc.accuracy, $overall.correct. That corresponds to $overall correct right there. I'm going to put the results into my save matrix. And so if I say save.results, now we have that first row completed. Let's now do this for all the remaining 10 rows. So I'm going to take this out, k equal 1, and run it. And this is what we get. So we have a lot of numerical values there. I mean, you could look through that table and figure out which values are best for k in terms of the accuracy. To be honest, it's best just to plot it. So let's do that. So we're going to plot the results first from using the validation data set. Actually, let me just show you the plots first. And that will make more sense than when we take a look at the code. Okay. So I'll blow this up too. On the right side, you have the results from the validation data set. Notice how I have everything nicely labeled. The dashed line there corresponds to the overall correct classification rate from using linear discriminant analysis that we've seen before. And so we can see that overall, that's the black line with the open circles. We can see that it tends to work a little bit better than linear discriminant analysis with respect to the validation data set. A little bit. It's questionable if that's enough to say, yeah, I prefer it. Especially once we take a look at some other results. The blue then corresponds to how well it's doing with the prediction of the successes. The reds, though, are for the failures. We can see we're having problems with the failures. So based upon the validation data set alone, if I had to choose a particular value of k, maybe 3 to 6, 7, because those are the highest for the overall classification rate. If it really meant a lot to you with respect to the successes or the failures, then you would focus on the blue or the red lines to make that kind of judgment. For the cross-validation, notice how the correct overall for linear discriminant analysis, when we did cross-validation, that tends to be better or about the same as using the nearest neighbor. So that's another thing that I would put in my head in terms of making a decision. There really isn't sufficient evidence to say that this is doing better, at least with respect to the cross-validation. Now, if I had to pick a k based upon cross-validation alone, then I would pick something like maybe 5 or higher. Now, let's say 5 and let's say 20 for k gave you exactly the same results, and these were the two best. Which do you think would be probably better to choose, 5 or 20? 5, because it makes things simpler. Think about all the computations that would need to be made if you had to do 20 versus 5. Okay? Basically a rule of thumb for statistics, when you're choosing like a model or choosing, in this case, a K, you choose the model, you choose the K here that is the simplest without sacrificing how good it's doing, how good the procedure is doing. Now, how did I do this plot? It's not too difficult. I use the plot function where I extract out the accuracy values from save.results. So the second column of save.results is the overall accuracy. The first, let me just double check that. I misspoke. The first column is the overall accuracy for, it's the accuracy for the failures. The second column is the accuracy for the failures. The first column is values of K. That goes on the x-axis. So I do my plot. Notice how I use a red color for the line and the plotting point. When I say type equal O, in R's terminology for the plot function, what that means is that I want not just the lines, but also the plotting points as well. If I did type equal quote L end quote, I would just get the lines, for example. Then I plot the results from the successes. I plot the results from the overall classification rate, where I use the points function to simply add points to a plot, add layers to the plot. I use the AB line function to draw a horizontal line at 0.8546, which corresponds to what we have for linear discriminant analysis. And then I create a nice legend at x equal 5, or well, actually it's k equal 5, and then the y-axis 0.8. Do a similar thing for cross-validation too. Okay, let me make sure I talked about everything here. So, you choose a K. And there's multiple Ks that are justifiable. I choose K equal 4. Here is the results from using K equal 4, where I use cross-validation. I get an overall correct classification rate of 0.8625. Notice this is a little bit different than what was actually in the plot. If you actually go back, you can see it's a little bit different. The reason being is because notice I have a different C number there. Why do I use a different C number? Well, remember when we started doing the for loop, we started at K equal 1. I set a C there. That C then helps then choose what happens for K equal 2, chooses for K equal 3, and so on. So I don't have a good way of coming back to what was the C then that was actually used for 4. And so I just chose a different C. Now, once you choose that K, you do the results that I just did there. Then, similar to what we did with discriminant analysis, we want to try to make sense of when it's working and when it's not working. And so what we can do is do a principal component score plot to help us visualize what's going on in 2 or 3 dimensions. And so this is what we get. The reds are the successes. The blacks are the failures. And again, I should have had a legend. And these are the predictions. if you remember, and I don't have it handy. I should have had it handy. We could go back to the original PC score plots that we had and actually look at what was observed and compare it to what occurs here. But one of the main reasons why I wanted to actually show you this particular plot, though, was notice how this differs from what we had with discriminant analysis. What was the weird characteristic that we had with discriminant analysis for this plot? Does anyone remember? There was like a black line on it. We could see how I drew a black line on the plot that showed how essentially to the left it was almost all reds, to the right was almost all blacks. That emphasized how discriminant analysis works, where it essentially draws a line to divide up the data. Here we don't see that. And so in situations where maybe a line might not be appropriate, this procedure could work better. Here's our 3D plot as well. Let's see, I did before class. I think I did it. Yep. So here's our 3D plot. And again, we don't see this like what instead of a line, what would be like a plane that divides everything up. We'd see some intermingling of the blacks and the reds for these predictions. Okay, let me see here. Hold on a second. So yeah, that was for cross-validation for the original data. What about if we use then the validation data set? So to now predict that validation data set, then I use KNN, train equals Z, test equals Z dot V. Excuse me, for K equal 4, I get 88.3% correct. Now, to do the principal component score plot for the validation data set, I need to do the principal components on the original model building data set. Then I use the predict function as what we've done before, and now apply it where new data is equal to valid. So I apply it to the validation data set. That's what I find the scores on. And this is what we get. Same that way essentially that we saw in the previous plot, but we just have less observations. Okay. Okay, some additional considerations then. What if you have more than two populations? Can you do this? Well, yeah. I mean, in fact, the original motivating example that I used had 3 populations. KNN.CV will work just fine. But the probability that you get back to you, though, will only be the probability for the actual group that the observation was classified into. It will not give you the probabilities for the groups that it was not classified into, which is different from what you saw for discriminant analysis when you saw those posterior probabilities. Now, another comparison between discriminant analysis and this. So for discriminant analysis, eventually you get that rule and you want to be able to apply it to new situations. Let's say a new field goal that's being attempted. All you need to actually retain from that original data set are the mean vectors and the covariance matrices to do that, to make that prediction. Now, what's interesting then here for K nearest neighbor, there's nothing you can throw away. You have to always retain the original data set itself because we're looking at how close is this new observation, this new field goal, is to all the other field goals that you've attempted in the past in that model building data set. So you cannot throw away the data set where you could with discriminant analysis. For very large data sets, as you might expect, some of the computations could take a long time. Because, let's say you have a million observations. Let's say you have a million observations, you're going to have to find a million distances for each observation that you want to predict. So there are algorithms that have been developed. And if you're interested in learning more about those, you can take a look at FNN package, stands for FAST, nearest neighbor. It has its own version of a KNN function. And it's similar to what was discussed earlier at the beginning. Observations for those K nearest neighbors can actually be weighted by how close they are to, let's say, that red dot that we saw. So something that's far away, that's still within the K nearest neighbors, will get a small weight. Something that's close by will get a large weight. And so there are ways to implement K nearest neighbor with that. Here is a particular function and package that implements those kinds of ideas. And then lastly, there are distance measures other than Euclidean distance that can be used. There's lots of different ways to measure distance other than Euclidean distance. And you're welcome to take a look at that function there. Okay, so that's all I have for K nearest neighbor classification. The concept is intuitive. There really isn't much to it. It can be a very useful procedure in the end. Only takes one day of class to go through it. So I think it would not be worthwhile to start a brand new topic with only the limited amount of time that we have. So let's talk about then what's next for our class. I will have office hours after class today. On Tuesday, we will start using something called logistic regression. Some of you may have seen it in another class before. We are focused here on using logistic regression for prediction. Is the place kick a success or failure? Rather than focusing on what variables affect the probability of success and trying to interpret that association. We're not interested in that at all. If you would be interested in that, take Stat 475, 875 next spring that I'm teaching in categorical data analysis. We will talk about project number 2, grading. I have a draft of project number 3. Maybe we'll get to that. So far it deals with the nearest neighbor stuff. Test number 3 is Thursday, December 4th. And again, project number 2 is due on Friday at noon. Please email it to me. When you email it to me, make sure to copy all the people in the group on the email so that after I grade it, I'll do reply to all, and then everyone gets back the graded project. Are there any questions? Okay, that's all for today then.